conditions. So the problem of the day we had last night was something called a Claisen condensation, and we'll talk about that a little bit more today, but let's go through and try to rationalize the mechanism here. I wouldn't just copy it out of the book. I tried to understand what's going on. Okay, so we've got sodium ethoxide, which is a strong base and a strong nucleophile. Can this do nucleophilic acyl substitution?
Yes.
Yeah, but does it matter?
No.
Because it gives you the exact same product out. So we could have ethoxide come in, attack into your ester, and then kick off your alcohol, but you get to the same product, right? You wouldn't be changing anything. So in this case, the only useful thing it can do is act as a base, and it will grab an alpha proton, and it will form your enolate. And let me actually change this slightly, and I'll make the equilibrium arrows a little bit more correct. So the equilibrium doesn't really favor the enolate that much, but just enough to make a good nucleophile. And then in the next step, we can have this add into the remaining ester that's around in solution. So we can get nucleophilic attack. Oh, I forgot my full ethyl group. There we go. And we end up with our addition product. What do you guys think the next step is?
Push down electrons and push off that O-ethyl group.
Yeah, we can push off our ethoxide, and when we do that, we reform a ketone.
See, I learned by looking at the books.
But a lot of this is very similar to nucleophilic acyl substitution that we've already seen.
It is.
Okay, so now we've got ethoxide around. What can that ethoxide do? Yeah, we still have a proton coming off of our alpha position. Ethoxide's still a good base. So in this case, it'll grab that alpha proton. Why doesn't it grab an alpha proton off of the methyl side of the ketone? It's more acidic. Why is that? Yeah, it's in between two carbonyl groups, which means that the conjugate base is highly resonance stabilized. The pKa of these alpha protons in particular is about 9. Oop. And you end up with a negative charge along with your ethanol. And then in the last step, we said we can react this with acid, and we can reform our final product. All right, so it's pretty simple. It looks a lot like our aldol condensation that we've already seen. And we're going to continue on talking about this today. Yep.
Should equilibrium arrows go throughout, or does it stop there?
Yeah, they are equilibrium arrows. The final product is very, very thermodynamically favorable. So oftentimes in your book, you'll see it as one-way arrows. This first reaction in particular, it is important to remember that that is in equilibrium conditions. If you reacted this with LDA, you would exclusively get your enolate, and there'd be nothing for it to add into. So in this case, ethoxide would be your preferred base. All right, so let's continue on to the Chapter 22 Claisen condensation section. And we'll briefly go over this again. So overall, we said that the reaction involves an ester forming an enolate and reacting with itself. And it's a two-step reaction. The first step is typically reaction with some sort of alkoxide. And then if we think about naming this final product, we can try to name it using our alpha-beta terminology. And so when we name this, we would call this a beta keto ester, because we've got a ketone coming off of the beta position. I've got a couple questions for you guys, though, before we jump into further stuff. Why are we using sodium ethoxide? Why not sodium methoxide? So Abby, you said something. How about somebody else too? Abby knows. But I want you guys all to think about this. Why do we need ethoxide?
You already answered it.
Well, do you guys hear?
Something about
She needs to say it again.
liquid.
Can you give us a
All right, Abby, let's be loud. Exactly. If we use another base like methoxide, we'd run into a mixture of products where you have a methyl ester instead of your ethyl ester. So in this case, you have to use the correct nucleophile, and usually it's the corresponding alkoxide to your ester.
Are you going to write that down?
Yep.
Thank you.
And that prevents any sort of substitution from occurring and making a new product. All right, next question I have, what's the purpose of the H3O+? Yeah, to reprotonate your enol. If you don't add in your H3O+, you'll be stuck with an enol product. So in this case, H3O+ is needed to protonate your enol. And this confuses a lot of people because you can get to the correct product without the addition of base when you draw out your mechanism, but your alkoxide is basic enough to deprotonate your alpha position once again, which I showed you guys on the problem of the day.
If you did it one and two, could you also add in
It wouldn't work very well. It'd be too sterically crowded. But yeah, that's a good question. It wouldn't work. We'll see when we get into alkylation that you can alkylate your alpha position more than once, but with the Claisen condensation, it gets too sterically crowded to add in two ketones off of there. All right, so I'm not going to redraw the mechanism since we already saw that on the problem of the day. I'll just say CPOD15, and then we'll continue on and look at some practice examples here. We saw crossed aldol condensation reactions yesterday. You can do the same thing with Claisen condensations too. So cross Claisen condensation. And with a cross Claisen condensation, you can use two different types of esters. And so let's take an example of this. What's the name of this ester? Yeah, methyl benzoate, right? Remember, you name the alkyl group coming off of your oxygen, and then you name the parent after that. So this would be methyl benzoate. And we can react this with a second ester. What base would we need? Yeah, sodium methoxide instead of ethoxide in this case. And then the second step that's also very important, we need to have our protonation step. So I want you guys to predict what the product would look like out of this. Do we have any alpha protons on methyl benzoate? No, so that can't act as the nucleophile in this case. If we look at our other ester, methyl acetate, this can act as a nucleophile because it does have alpha protons. So if we were to go through and deprotonate that alpha position, it could add into methyl benzoate and kick off methoxide. So our final product would be our beta keto ester, where this carbon, the green one, added into the electrophilic center on methyl benzoate and then kicked off methoxide as the leaving group. So if it does help you to draw the mechanism, I would encourage you to do so. Oftentimes, once you get used to these, you can just start predicting what the product looks like without the mechanism. One thing I will say is that you have to be very careful with your choice of reagents here, right? Just like with aldol condensations, you can run into mixtures. So we had the example yesterday where we didn't choose our reagents very carefully and we ran into 4 different products. But there's a few different ways we can control this. The first one is you can use only one type of ester, which really isn't a cross Claisen condensation, it's just a Claisen condensation. Or you can do route 2, where you use the Lda method. And do you guys remember the Lda method from yesterday? Yeah, exactly. So you take one ester with alpha protons, you drip it into Lda, make that the enolate exclusively, and then add your second ester. So add first ester to Lda, then add your second ester. So that's another method. Or we can use a method like we saw above, where we're careful to only have one reagent with alpha protons. So these are all ways to avoid mixed products for not only Claisen condensations, but aldol condensations as well. All right, now I've got a more challenging problem for you guys. All right, so I want you to determine what you think the main product would be for this Claisen condensation. So I'll give you guys a minute to work on this. What's special about this?
It's symmetrical.
It's symmetric and it's got 2 esters on itself. So what do you think might happen? There's a couple ideas. Yeah, it could close and attack itself, right?
Could you also have a product where you added twice to both of them?
We'll talk about that, but try to do the ring closing first.
Because that's what it's going to do.
Because that's what it's going to do.
Would it also do the other one?
Let's first do the mechanism, and then we'll ask ourselves why that's probably not likely that it will form a long chain. I'll give you a hint, though. Entropy.
I think it would work with the other way too. I don't see what would stop
All right, I'll just tell you right now. I'll give you the rationale for why it's not forming a long chain. Does the universe want to become more ordered?
No.
No, it wants to become more disordered. So having two molecules come together and reacting creates more order. That's not as favored as a cyclization reaction.
But I feel like the ring would still create more order.
It does, but not as much as having two molecules coming together. All you're doing is limiting rotational freedom. You're not converting 2 moles into 1 mole.
Why wouldn't you want to be more ordered? I'd rather have more order in my life. I just don't understand, like, why that's the law.
The universe is a chaotic place.
But you just made that up.
All right, so let's go through and quickly do the mechanism for this. I'm just going to pick these alpha protons. We could have deprotonated from the other side too. Okay. All right, so we've got our enolate now. And our enolate can actually attack into the other side of your ester. And this time let's count. We'll go 1, 2, 3, 4, 5. Okay, 5-membered rings are pretty stable, so that seems all right to me. So I'll number this new ring. We've got 1, 2, 3, 4, 5. If we look off of the 1 position, we've still got an ester group dangling off. If we look off of the 5 position, we've got a oxygen with a negative charge, and then we've got a ethoxide.
You scared it's not coming to play at all in that though? I think a little bit.
I mean, it's a little bit crowded, but what's happening in the next step? Yep, exactly. So we can clamp down, kick off our ethoxide. And intramolecular cyclizations are very, very favorable due to the entropic considerations compared to having 2 molecules attack one another. Okay, and then we've got ETO negative. What will this do?
Grab another proton.
Yeah, we've got another alpha proton here.
Alcohol.
So we're almost there. We've got our enolate. And our last step is going to be our protonation. Do you guys ever watch TV and see somebody with an invention and you're like, that was such a simple idea, why didn't I think of this first?
Yeah.
This guy actually got the reaction named after him when everybody was like, well, yeah, like, of course you can do that. It's just a Claisen condensation. But this is actually named after the scientist who worked on it, and so it's called a Diekman Cyclization. I'm jealous that I don't have a reaction named after me yet. But really, a Diekman cyclization is just an...
First, we talked about this, you have the potential.
Yeah. They're still young. It's going to happen.
We're holding you back.
No, all the easy reactions, I think, more or less got claimed already. It's an intramolecular
You should start kicking in once you have a reaction of your own.
Claisen condensation.
Different topic.
That's all you teach.
Yeah, just my named reaction.
Cyclization.
All right, so the Diekman cyclization is this unique example of a Claisen condensation. What rings are preferred if you're doing a Diekman cyclization? 5 or 6. So in this case, the thing to remember is it prefers 5 or 6 membered rings. So you don't see a Diekman cyclization where your final product is a 4-membered ring. In that case, you would get the longer chain instead of the cyclization product. All right, so let's do a couple practice problems with these two. So let's do one practice problem that's a synthesis problem.
Why 5 or 6?
If we get into really large or really small rings, you run into ring strain.
Larger rings than 6?
Yep, large rings have ring strain too. That and you run into a higher likelihood of forming polymers. Yeah. So in this case, 5 and 6 membered rings are highly favorable. All right, so let's look at this practice problem for synthesis. That's not a joke. How could we make this
Name this.
from the Claisen condensation?
Oh, we're going backwards?
So what I would do is just take a step back and ask yourself which carbon acts as the nucleophile.
One in the middle.
Yeah, the one in the middle, right? So in this case, this green carbon acted as a nucleophile. Which carbonyl group did it add into? The ketone or the ester? The ketone, right? So in this case, the bond that we're first forming, or last making, I should say, would be that bond. So we have to ask ourselves, what 2 esters would we need?
Wait a minute. How do you know that it went into the ketone?
So if you, okay, let me scroll up really quick. Nope, it's cyclohexane. If you look at this carbon acted as the nucleophile, and it attacked here. So the thing that it attacked ultimately became a ketone.
Okay.
So if we look at our problem that we had, this carbon that's in green is attached to a ketone, which means this was the carbon that was attacked. So let's first determine which 2 esters we need, and then we can develop a scheme in the forward direction.
Benzoate and
Mm-hmm. All right. So it looks like a few people are there. What I would do that would be 1 ester. And this would be our other ester, right? So in this case, this alpha proton, or that alpha position, can attack our carbonyl position once it's deprotonated and kick off that ester group, right? So these would be our 2 esters. Now we have to ask ourselves, how would we do this in the forward reaction? Would we need to follow any specific order, or can we just toss in hydroxide? What should we do? Sodium ethoxide, right? So in this case, we don't have to worry about using LDA because only one product has alpha protons. So we don't need to worry about getting crossed or mixed products. So what I would do is just take both of our esters, which was ethyl benzoate, and our ethyl, I'm actually not sure how to name the cyclohexane derivative. I have to look that up.
You lost the card.
Oh,
First one.
I did, thank you. There we go. I'd have to look up how to name that one. And then we treat this with sodium ethoxide, followed by acid, and that would give us our final product. So this would be our synthesis scheme. All right, let's do another practice one.
And you pick the sodium ethoxide because the ethyl's coming off.
Yeah, so what you should do is look at what's going to be your leaving group. In this case, it would be ethoxide. In this case, it would be ethoxide. You want your base that you're using to be the same, alkoxide, as your leaving group. All right, let's do another practice problem. But this time, I want you to provide the mechanism. So this one looks a little funky. So we do first sodium ethoxide followed by acid.
Why do you keep picking these crazy little ones?
Oh, shoot, I messed this up. Sorry. It should be over one more carbon. There we go.
Yeah.
Now we can have it. Yeah.
Where's your pencil cream? So this has two esters in the same molecule. What do you think might happen? A ring closing again. So this would be an example of a Diekman cyclization. So we've got alpha protons on either position. It doesn't matter which one we choose. They're chemically equivalent. So I'm going to help you guys with the mechanism here. We've got ethoxide around. This can come grab an alpha proton. And then it can wrap around and attack itself. But before we show the product, let's try to number things and make sure we're keeping track of what's going on. We've got 1, 2, 3, 4, 5. So 5 membered rings would be fairly stable. And this is coming off of a benzene ring. And so I'll renumber our ring system. We've got 1, 2, 3, 4, 5. Let me actually move this 1 over a bit. And then off of our 1 position, we've got our ester. If we look over to our 5 position, we've got an oxygen with a negative charge. And we've got an ethoxy group. What do you think the next step is? The malicious shove. So it'll kick off our ethoxide. Nope, sorry. I was losing focus there. So now we've got our final product, but we have something else going on in the meantime. What's the step we shouldn't forget about? Yeah, it doesn't stop here in the reaction. You have an uncontrollable acid-base reaction. And you've got a negative charge there, which in your last step you can reprotonate with an acid. So this would be an example of a Diekman cyclization. The final products always look scary from these condensation reactions, but just try to break them apart and do the full mechanism for them, and that should help you quite a bit. Are there any questions with the Claisen condensation? It's very, very similar to the aldol. So if you can master the aldol, you're pretty much set for the Claisen condensation too. All right, so let's continue on to alkylation in the alpha position. Slightly different, but it's all variations on the same theme. And the overall mechanism is very straightforward. If you have a ketone, and in this case I'm just picking cyclohexanone, you can treat it with a base. And then in the next step, you can treat it with some sort of alkyl group. So in this case, an alkyl halide. When you do this, you can alkylate in your alpha position. Pretty straightforward. Do you guys want to see the mechanism for this?
Yes.
All right, the mechanism's nice and easy. So the most acidic protons on these are your alpha position protons. So in the first step, if you've got a base, I'm just going to call this base B-. This base can come grab an alpha proton, form your enolate. And then this enolate can attack your alkyl halide. Kick off your leaving group, and you get alpha halogenation. We'll talk about that. These are actually fairly easy to control just based on how many equivalents of your alkyl halide you add, right? So reaction stoichiometry does matter in these cases. If you added in a ton of base and a ton of your alkyl halide, then you could do this multiple times. And we'll talk about that. But I've got a second question for you guys now. And this tricky question is, we had cyclohexanone, but what if we had a methyl cyclohexanone, 2-methyl cyclohexanone? And we first react this with base, and then we react it with our alkyl group, or alkyl halide. What will our product be?
I want to be on the left side.
So let's draw out both potential products, because we've got two different alpha positions. You could have one where your alkyl group installs next to the methyl group, so let me finish drawing these out. Or one where it installs on the opposite side, so you could have your alkyl group there or there. Which one do you think we would get and why?
The left one.
The left one is more substitute.
It gets a little bit complicated here, but let's think about the mechanism for each. So I'm going to actually slide this down a bit. Sorry. If you think about the intermediate for these, the top one goes through the more stable intermediate, right? The bottom one, goes through an enolate that's less substituted. So this brings into play thermodynamics, right, and kinetics. If we look at this one, it's the more stable enolate, which means it has a lower activation energy. If we look at this enolate, we could say that this one is less stable. Actually, sorry, let me erase the EA part, and we'll just focus on the stability of the enolates right now.
But is that true? It's lower.
Well, let's take a look at a different question now, before we get there. Which alpha proton is more accessible? So let me clarify what I mean by this. If we're looking at these alpha protons versus that alpha proton, which one's more accessible? The one on the left. The blue one. All right? So if we're thinking about accessibility, which is the more accessible enolate?
The less stable.
Yeah, exactly. So this one's has more accessible enolate. So in this case, it actually has a lower activation energy. My notes were flipped. And if we look at this top one, we would say that this one is the less accessible enolate. Its proton in that alpha position is harder to grab. So now we've run into a situation. If we look at the product on the left here, this product, is that going to be our thermodynamic or our kinetic product? Thermodynamic. So it goes through the more stable enolate, but its protons are harder to get at, so it's got a higher activation energy. On the other end of the spectrum, we've got our kinetic enolate, or kinetic product. Uh-oh. Sorry, just 1 second. Shoot. Dynamic. product. All right, so does that make sense? We've got two different things going on. We've got accessibility of our alpha protons, and then we've got stability of our enolates. Those are two competing things at play here. So how can we favor formation of thermodynamic products? Add heat. What about kinetic products? Run it really, really cold. What about our base even? If we want our thermodynamic product, do we want a really big base or a really small base? Small base. We want something that can be small enough to reach in and grab that alpha proton. If we want our kinetic product, do we want a really big base or really small base? A big base. So we've got a couple of things we can use to control this reaction. So if we do LDA, is that a big or a small base? It's a big base. And we would want to run this cold. Specifically, I would say we'd want to run this at negative 78 degrees.
Pretty specific.
That's pretty specific. I'll explain why. Does anybody know what negative 78 degrees represents in terms of practical lab supplies?
Sure don't.
Oh, that's when stuff stops working.
So ice is 0 degrees. What's colder than ice?
Dry ice.
Oh, dry ice. So in this case, lots of labs have dry ice. And what they do is they get a big thing of acetone, which is nice and cheap, and they hunk dry ice in. It looks like a Halloween type thing, but it actually stays at a perfect negative 78 degrees Celsius. And it can be done to control kinetic reaction. So you can use LDA, and you can get your kinetic product. Or we can try to get our thermodynamic product. We're going to run this at room temperature. And what's a nice small base we can use?
Sodium hydride.
Yeah. Sodium hydride is really popular for this reaction because it's capable of abstracting the proton on the less accessible side much more easily than LDA. And I'm going to even circle this and try to emphasize that this can attack the less hindered, or sorry, it can attack the more hindered alpha proton. LDA, on the other hand, has a hard time. Alpha proton. All right, so that's kind of the trick that chemists use to control alpha alkylation, is they can choose the size of their base and the temperature of the reaction. All right, tomorrow we'll continue on with the malonic ester synthesis, and it's really similar to this. Your problem of the day is a reaction that's actually not in your book, so you can't look it up. But I gave you guys step-by-step directions on how to go through it, and it's very similar to aldol chemistry.
But still, I like